Green infrastructure, GI, connectivity plays a crucial role in shaping sustainable, resilient, and livable cities in the 21st century. As urbanization accelerates globally, natural systems are increasingly fragmented by roads, buildings, and other gray infrastructure. This fragmentation disrupts ecological processes such as species migration, water cycles, and climate regulation. By intentionally linking parks, waterways, wetlands, ecological corridors, urban forests, and public open spaces, cities can maintain and even restore natural processes within densely built environments. Connectivity transforms isolated green patches into functioning ecological networks that provide cumulative environmental, social, and economic benefits. Connected GI systems strengthen biodiversity by enabling species movement between habitats, increasing genetic diversity, and improving ecosystem resilience to disturbances. They also mitigate climate impacts by reducing urban heat island effects, enhancing stormwater infiltration, and storing carbon in vegetation and soils. Equally important are the social dimensions. Accessible green corridors improve mental and physical health, encourage active mobility, and foster social interaction. In many cities, green connectivity also addresses spatial inequalities by improving access to nature in underserved neighborhoods. In this lecture, we explore how different cities address ecological fragmentation and implement nature-based solutions at multiple spatial scales. Through case studies from London, Seoul, and Nairobi, we examine how planning systems, governance models, funding mechanisms, and community participation influence outcomes. These examples demonstrate that multifunctional GI can simultaneously address ecological resilience, climate adaptation, mobility, public health, and social cohesion. Together, they highlight the transformative potential of connected green networks in contemporary urban development. The All-London Green Grid, ALGG, represents a strategic planning framework that integrates green and blue infrastructure across the entire metropolitan region of London. Rather than treating parks and waterways as isolated amenities, the ALGG envisions them as interconnected components of a citywide ecological system. Its overarching goal is to create a continuous network of parks, river corridors, woodlands, wetlands, street trees, and active mobility routes that function cohesively across borough boundaries. The ALGG seeks to improve access to high-quality green spaces for all residents, particularly those living in areas historically lacking investment in environmental infrastructure. By identifying opportunity areas and strategic corridors, the framework directs investment toward neighborhoods with limited access to nature. Ecologically, it strengthens habitat connectivity by linking fragmented sites, allowing species to move more freely across the metropolitan landscape. Socially, it integrates walking and cycling paths, supporting healthier and more sustainable mobility patterns. Through large-scale coordination and alignment with spatial planning policies, the ALGG helps London address climate resilience, reduce health inequalities, and promote sustainable urban growth. It demonstrates how strategic, metropolitan-scale GI planning can transform everyday experiences of nature while reinforcing long-term sustainability objectives. London's Green Grid significantly enhances ecosystem services across the urban landscape. The connected network moderates urban heat through shading, evapotranspiration, and increased airflow, reducing the severity of extreme heat events that are becoming more frequent due to climate change. Street trees, parks, and river corridors collectively lower surface temperatures, contributing to public health and energy efficiency. Stormwater management is another key benefit. By restoring floodplains, enhancing permeable surfaces, and reconnecting rivers to natural systems, the network enables water infiltration and reduces pressure on conventional drainage infrastructure. This is particularly important in a city vulnerable to both surface water flooding and river flooding. Habitat connectivity promotes species movement and ecological resilience. Green corridors link urban woodlands, wetlands, and parks, supporting birds, pollinators, and small mammals. Biodiversity gains strengthen ecosystem stability and enhance cultural appreciation of urban nature. Social ecosystem services are equally vital. Access to green spaces correlates with reduced stress, improved mental well-being, and increased physical activity. The ALGG therefore supports London's long-term sustainability goals through reinforcing ecological and social benefits that extend beyond individual sites. Governance is central to the success of the ALGG. The metropolitan strategy aligns with the statutory planning framework of the London Plan, ensuring that all boroughs work toward shared green infrastructure objectives. This policy alignment creates consistency in development control, land use planning, and infrastructure investment. Funding mechanisms combine public investment, developer contributions, and partnerships with environmental organizations. Design guidelines provide quality standards for biodiversity, accessibility, and resilience. Implementation tools ensure monitoring and accountability. Cross-sector collaboration strengthens project outcomes. Urban planners, ecologists, engineers, landscape architects, public health professionals, and community groups contribute expertise. This interdisciplinary cooperation ensures that projects address multiple objectives rather than serving single-purpose functions. Continuity across political cycles is also crucial. Large-scale GI networks require long-term commitment extending beyond electoral terms. Institutional structures provide stability, allowing projects to mature over decades. London's governance model illustrates how coordinated multi-level policy can effectively support ecological integrity and social well-being. The Changyicheon Restoration in Seoul stands as one of the most influential examples of urban ecological regeneration. Historically, the stream was covered by concrete and later overshadowed by an elevated highway constructed during rapid industrialization. By the late 20th century, the area suffered from traffic congestion, pollution, and declining urban quality. The restoration project removed the elevated highway and daylighted the buried river, transforming it into a vibrant ecological and social corridor stretching through downtown Seoul. The intervention reconnected previously fragmented neighborhoods and dramatically improved walkability. Changyicheon symbolized a paradigm shift, prioritizing ecological restoration and human-centered design over car-dominated infrastructure. The corridor attracts millions of visitors annually, demonstrating strong public acceptance and economic revitalization. It has become a global model for cities seeking to reverse environmental degradation and reclaim urban waterways. The restored Changyicheon corridor functions as a major active mobility spine through central Seoul. Dedicated pedestrian pathways and cycling routes encourage non-motorized movement across the dense urban core. By prioritizing walkability, the project promotes healthier daily routines and reduces reliance on private vehicles. The presence of flowing water and dense vegetation creates a cooler microclimate. Studies indicate temperature reductions of several degrees Celsius compared to surrounding streets during summer months. This cooling effect improves thermal comfort and demonstrates the climate adaptation potential of urban blue-green infrastructure. Public spaces along the corridor support leisure activities, cultural events, art installations, and informal social gatherings. The combination of ecological restoration and high-quality public realm design has transformed Changyicheon into both an environmental asset and a central civic space that enhances everyday urban life. Post-restoration monitoring revealed substantial increases in biodiversity, including fish, birds, amphibians, and insects. Improved water circulation restored ecological processes and habitat formation. Air circulation along the corridor reduces pollutant concentrations and improves ventilation in the dense urban core. The naturalized channel enhances flood resilience by accommodating stormwater during heavy rainfall events. These outcomes show that renaturalization strategies can outperform conventional gray infrastructure. Rather than relying solely on underground drainage systems, ecological design integrates hydrological and climatic adaptation directly into public space. The Nairobi Green Line initiative in Nairobi creates a protective ecological buffer between the city and Nairobi National Park. As urban expansion intensifies, pressure on park boundaries increases. Informal settlements, infrastructure projects, and illegal land use threaten ecological integrity. The Green Line establishes a continuous tree-planted corridor that stabilizes soil, reduces encroachment, and enhances habitat quality. Beyond physical protection, it raises awareness about conservation and strengthens the symbolic connection between urban residents and wildlife. This initiative positions Nairobi as a city actively preserving its natural heritage despite rapid urban growth. The Green Line is driven by a coalition of government agencies, conservation NGOs, private corporations, and community volunteers. Tree planting campaigns mobilize citizens, schools, and local organizations, building strong community ownership of the project. Corporate sponsorship provides financial resources and logistical support, while environmental NGOs contribute technical expertise in species selection and ecological monitoring. Collaborative governance ensures long-term maintenance, which is critical for the survival of planted trees in semi-arid conditions. This partnership model fosters environmental stewardship and strengthens social cohesion. It demonstrates how community-driven initiatives, supported by institutional frameworks, can achieve large-scale ecological outcomes. The Green Line improves environmental quality by reducing dust, absorbing pollutants, and buffering noise from nearby roads and development. The expanding tree canopy enhances microclimatic regulation, moderating temperatures and retaining soil moisture in otherwise dry conditions. Additional vegetation provides supplementary habitat and movement pathways for wildlife species moving between the park and surrounding landscapes. These ecological benefits also improve living conditions for nearby communities by enhancing air quality and visual amenity. The Green Line highlights the importance of protecting ecological interfaces in rapidly expanding cities. Even relatively low-cost, nature-based interventions can generate substantial environmental and social value when strategically implemented. The three case studies differ significantly in spatial scale, governance reach, ecological complexity, and socio-economic context. Understanding these differences is fundamental to designing appropriate green infrastructure (GI) strategies. In London, GI connectivity operates at a metropolitan scale. The All-London Green Grid coordinates ecological corridors, parks, river systems, and mobility networks across a vast urban territory of more than 8 million inhabitants. The scale requires cross-borough collaboration, long-term spatial planning instruments, and strong regulatory alignment. Connectivity here is not limited to individual projects. It is embedded in strategic planning frameworks that shape land use, transport infrastructure, housing growth, and environmental management. The metropolitan scale allows cumulative ecosystem service delivery but demands institutional capacity and policy continuity. In contrast, Seoul focuses on a linear, corridor-scale intervention within a dense urban core. The Chongyicheon stream restoration demonstrates how a single, high-impact project can catalyze systemic change. Although geographically smaller than London's grid, the intervention reshaped mobility patterns, economic activity, microclimate regulation, and ecological restoration in central Seoul. This case illustrates how concentrated investment in a strategic corridor can generate citywide ripple effects. Meanwhile, Nairobi addresses GI connectivity at the urban ecological boundary scale. The Nairobi Green Line functions as a buffer between the expanding city and Nairobi National Park. Here, connectivity is less about internal urban networks and more about protecting ecological integrity at the interface between built and protected landscapes. The spatial logic is defensive and preventative, focusing on containment, conservation, and awareness. These scale differences demonstrate that GI connectivity is not a uniform concept. It must respond to urban density and morphology, ecological sensitivity and biodiversity value, governance capacity, economic resources, climate vulnerability. Recognizing scale allows planners to select appropriate tools, from policy frameworks and zoning regulations to corridor design and community planting initiatives. Effective GI planning therefore begins with understanding spatial context. Governance structures fundamentally shape how green infrastructure projects are conceived, funded, implemented, and maintained. Comparing the three cases reveals different institutional pathways toward ecological connectivity. In London, governance is policy-led and embedded within statutory planning. The Greater London Authority provides strategic direction through the London Plan, ensuring GI integration across borough development plans. This model emphasizes regulatory consistency, monitoring systems, and alignment between environmental and urban growth objectives. The advantage of such a structure lies in stability and long-term continuity. However, it also requires administrative coordination and political consensus across multiple jurisdictions. Seoul's Cheonggyecheon restoration represents a governance model driven by strong political leadership and executive decision-making. The project required removal of major transport infrastructure, substantial financial investment, and rapid construction. Political will enabled swift implementation, but it also required extensive public consultation to mitigate resistance from businesses and commuters. This case demonstrates how transformative GI projects often depend on visionary leadership combined with technical expertise. Nairobi's Green Line highlights a collaborative and grassroots-oriented governance model. While supported by governmental and institutional actors, much of its energy comes from NGOs, volunteers, schools, and corporate sponsors. This model fosters community ownership and environmental stewardship but may face funding variability and long-term maintenance challenges. Institutional partnerships help stabilize these risks. Governance influences, funding mechanisms, speed of implementation, degree of public participation, transparency and accountability, long-term maintenance capacity. For GI to succeed, governance must integrate ecological knowledge, planning regulations, and community engagement. Institutional strength determines whether green infrastructure remains symbolic or becomes embedded in urban systems. While green infrastructure delivers multiple benefits, it is not without trade-offs. Effective GI planning requires acknowledging and managing potential conflicts and unintended consequences. One common trade-off involves land use competition. Urban land is scarce and expensive. Allocating space for ecological corridors may compete with housing, commercial development, or transport expansion. In London, balancing growth targets with habitat preservation requires careful spatial prioritization. In Seoul, removing a highway disrupted traffic systems and required transport reconfiguration. In Nairobi, protecting park boundaries may limit certain development opportunities. Another risk is green gentrification. High-quality green spaces can increase property values, potentially displacing lower-income residents. While improved environmental quality is positive, equity considerations must be integrated into planning to ensure inclusive access and prevent socio-spatial inequality. Financial constraints also shape GI feasibility. Large-scale restoration projects require significant upfront investment, even if long-term ecosystem services generate savings. Securing diversified funding sources is therefore essential. Adaptive management becomes critical in addressing these challenges. This includes continuous ecological monitoring, stakeholder feedback mechanisms, policy adjustment over time, scenario planning for climate uncertainty. Ecosystem service assessments help quantify benefits such as flood mitigation, cooling, air purification, and health improvements. Such evidence supports transparent decision-making and strengthens the case for investment. Ultimately, trade-offs should not deter GI development but rather encourage inclusive, data-driven, and flexible planning approaches. The case studies collectively demonstrate that connected GI networks are inherently multifunctional. They operate as ecological systems, social spaces, climate adaptation tools, and economic catalysts simultaneously. In London, the Metropolitan Grid links biodiversity enhancement with sustainable mobility and public health strategies. In Seoul, Cheonggyecheon integrates microclimate regulation, tourism, recreation, and ecological restoration within a single corridor. In Nairobi, the Green Line combines conservation, community engagement, and landscape stabilization. Multifunctionality increases resilience because benefits reinforce one another. For example, trees provide shade, climate adaptation, improve air quality, public health, and enhance biodiversity, ecological resilience. River restoration reduces flood risk while creating recreational spaces and supporting aquatic ecosystems. Green corridors promote physical activity and reduce emissions by encouraging active transport. Systems thinking is essential to designing such networks. Rather than treating parks, rivers, and trees as isolated amenities, planners must view them as interconnected components of urban metabolism, influencing energy flows, water cycles, biodiversity, and social interaction. Long-term visions are critical. Vegetation growth, habitat maturation, and climate adaptation unfold over decades. GI planning must therefore extend beyond electoral cycles and short-term investment horizons. These lessons are transferable across global contexts, demonstrating that ecological connectivity strengthens urban sustainability strategies regardless of geography. Effective green infrastructure implementation depends on several interrelated principles. First, stable and diversified funding ensures continuity. Public budgets, private partnerships, grants, and community contributions can collectively support implementation and maintenance. Without sustained investment, ecological gains may deteriorate over time. Second, supportive governance frameworks institutionalize GI as essential infrastructure. When embedded in statutory planning documents, building codes, and climate adaptation strategies, GI becomes a structural component of city development rather than an optional enhancement. Third, community engagement fosters ownership and long-term care. Residents who participate in design and maintenance are more likely to protect and value green spaces. Nairobi's volunteer-driven planting campaigns illustrate how engagement strengthens stewardship. Fourth, design excellence balances ecological function with cultural identity, safety, and accessibility. Successful GI is not only biodiverse but also inclusive, welcoming, and context-sensitive. A well-designed corridor must accommodate diverse users, children, elderly residents, commuters, and visitors. Finally, adaptability ensures resilience in changing environmental and socio-economic conditions. Climate change, demographic shifts, and technological innovation will reshape cities. GI must evolve accordingly. These principles reinforce the idea that green infrastructure is not decorative landscaping. It is critical urban infrastructure that underpins environmental security and social well-being. For EPD-Net learners, the examined case studies provide practical and theoretical foundations for developing GI connectivity expertise. They demonstrate how scientific research, ecological modeling, and climate projections translate into real-world planning and design interventions. Students can use these examples to analyze governance effectiveness, risk assessment strategies, stakeholder engagement processes, ecosystem service valuation, spatial planning integration. Developing competencies in systems thinking enables practitioners to understand complex interdependencies between built and natural systems. Resilience planning skills allow professionals to anticipate climate risks and design adaptive solutions. Participatory methods ensure inclusive processes that reflect community needs. Exposure to diverse global contexts, from metropolitan Europe to East Asian megacities and African conservation interfaces, strengthens cultural awareness and problem-solving flexibility. It prepares future planners, designers, and policymakers to tailor GI solutions to varied socio-economic and climatic conditions. Ultimately, these insights support the development of urban practitioners capable of integrating ecology, governance, design, and social equity into coherent green infrastructure strategies. Connected GI networks are foundational to sustainable urban futures, and building expertise in this field is essential for addressing the environmental challenges of the coming decades.